Hey there, Calc 3 folks. I hope you're hanging in there. One of the things we are going to do this semester is to kind of help cope with having to move over to online studies for the remainder of the semester. I'm going to try to put together some lectures here. You might say a lecture series over our remaining two chapters, Chapter 16 and Chapter 17. So what I'm going to do here today for you is the first video in that series of lectures, and this is pertaining to Chapter 16, where we look at 16.1 material and we introduce double integrals over rectangular regions. I will note is that before we left for break on that Monday, before we had our test number 2, I did lecture over this material, giving you some insight into double integration, right? What we're going to learn a little later on in Chapter 17 is what's also known as surface integral. We're going to, what I want to do here for you is make sure that I give you a complete set of lectures. So I do want to go back and maybe start in 16.1 again and give you the beginnings of what would be a then complete lecture over multiple integrations in Calculus 3 that is all available online. There's nothing worse than missing that first 15 minutes to the movie and trying to figure out what the plot is. So I will do that here in this video. All right. So one of the ways I'm going to present here is I'm going to just really present my notes. I'm going to kind of run down these like I would be on a whiteboard in front of you. What's kind of nice is I have organized things here to begin with. I can give you some really nice illustration when I can get all that together. And then, right, it's certainly, compared to my handwriting, a little bit more legible. So to begin with, here in Chapter 16, we are talking about multiple integrals, and what we did on that day before the break, where we spent a little time introducing these concepts, is we did take some note on what we understand as single integration, right? Which I pointed out is also known as linear integration. And it involves the application of this operator, right? This operator, the integral from a to b for dx being applied to some function. And what we considered applying it to was the multivariable function f, which was contained in three-dimensional space here, right? Which was an element of the three-dimensional system, right? And we can apply this operator to function f, as we had noted, where the result was a net area function of y. Right? If we're dealing with a multivariable function f of x comma y, and we integrate that function with respect to x over these bounds from a to b with respect to x, the result is a single variable function, which we know as a net area function. What we could highlight in between here is we are finding big F at x comma y, right? And evaluating it across the bounds from a to b, which does involve evaluating big F at the value of for the value of b for x comma y, and subtracting from it the value of big F evaluated at the quantity a for x comma y, right? Where we might point out then, big F's first partial with respect to x for x comma y would be equal to little f of x comma y, right? And this net area function g that we have as a result, when we evaluate it at y null, this describes the net area trapped between the surface z equal to f of x comma y and the xy plane over a line segment in the xy plane at y equal to y null. And this would be for values of x in this closed interval from a to b. To explore what I'm saying here, we might consider an example. For example, right, we might consider the net area function for the area space trapped between this function here, given by 1 plus x plus y, and the xy plane, at some arbitrary value of y for values of x in the closed interval from 1 to 6. This is going to produce a net area function, right? And the value of this net area function is going to be given by a linear integration. Applying that linear integral operator to this function will produce the surface F will produce this net area function g of y. If we apply this linear integral operator, right, to function f, it is going to produce this net area description here. Right? That is specific to some arbitrary value of y. Right? In our integration process, that linear integral applied to this function with respect to x does produce this quantity as its antiderivative. Now keep in mind, we went through this. This is treating only variable x as a variable, right? That's the variable of interest in our integration here. And we are integrating everything else that doesn't involve x as a constant value. So this value of 1 is treated like a constant, and its integral with respect to x is x. And this quantity y is treated like a constant. So its integral with respect to x is x times y. As for x's antiderivative, that is 1/2 x squared. Right? So applying that integral across this function, right, yields this antiderivative, right? That is, right, what we might say this statement being made, where we understand big F is going to be the antiderivative of little f. It's a function here that we've produced, where when we take the partial with respect to x, it does yield this quantity 1 plus x plus y. Right? And you can see that would be the result if you took the partial of this quantity with respect to x. Now what this notation does highlight, right, is we are going to want to then evaluate that antiderivative across these bounds from a to b. We are going to want to evaluate it at the upper bound of b and take away from that the value of big F at the upper bound of a. Now these being bounds that involve the quantity of x, the variable x, right? We are replacing x with those values. So if I replace 6 into this quantity, right, that will simplify to 24 plus 6y. And if I replace 1 into this quantity for x, that will replace 3/2 plus y. Oh, that will become 3/2 plus y. So if I then take the difference of those two quantities, it simplifies to this linear argument, 45/2 plus 5 times y. And what 45/2 plus 5 times y describes, we'll take note, bring this into view. Right? This is going to describe the net area function. Right? The net area function that we were looking for in the problem, right? G of y. It tells us the area trapped between the surface and the xy plane, right, at some arbitrary value of y over values of x in this interval from 1 to 6. So if we were to consider it at a very specific value of y, if we were to consider it at the case for y equal to 3, right, that net area would simply be given by evaluating function g at 3, which is 45/2 plus 5 times 3, which does become 75/2 units squared. We are talking area, so it is a measurement of units squared. And if we want an illustration of that net area, I would scroll down here, right? And you'll notice I do present you with this illustration. Now, what are we illustrating? If I was to scroll up and perhaps, let's open this a little bigger so we can see it a little bit more clearly. Right? The light gray surface that we see with this mesh passing through it, this rectangular mesh or square mesh, helping to illustrate that surface, that is the surface 1 plus x plus y. That is our surface in three-dimensional space. What we are doing is integrating over that surface, right, or we might say across that surface, over this line that exists down in 2 dimensions, right? Here we have our xy coordinate plane at the base of this cube, right, where our surface is forming. This cube illustrating what we might think is highlighting octant 1 in three-dimensional space, where x, y, and z are all positive in value, and we see that described out on our axes. Where in that xy plane, we do have this line forming in the xy plane. This line that forms at the value of y equal to 3. Notice that is where we are considering our net area calculation occurring. Is that a case of y equals to 3, halfway between 2 and 4 here on the y-axis, over values of x that happened, if we go back in the problem, across the bounds of x from 1 to 6. So we can see that in our illustration down here, right, with this bound happening at the value of 1 and this bound happening at the value of 6. That is going to help to define this line here in the xy plane of three-dimensional space, where what we're calculating is the area trapped between this surface in 3 dimensions and this line in 2. That area we're calculating is illustrated by this shaded area here. This area that's happening in the middle of our graph that appears to be kind of more of a bluish color, trapped between these two magenta lines, right? Those two magenta lines, again, here's our y-axis, here's our x-axis, here's our z-axis. Y at 3, x from 2 to 6. We're integrating over this line, right, across this surface, and what we're calculating is this net area, right? I just realized my cursor wasn't showing up as I gave you that description, but we are looking at this area forming along this planar surface in three-dimensional space that really is this planar surface, the section of a plane that's to trap between this surface in 3 dimensions and this line down here in the xy plane in 2-dimensional space, right? That net area is 75 halves units squared, all right? Folks, when we apply a linear integral, right? When we apply a single integral operator to a function, we are applying what we call a linear integral. We are performing an integration, right, that is going to occur across some line. And what we're going to see is that line can be defined, right, here in 2-dimensional space as we've defined it in this particular scenario. But it does come from an understanding that developed back in Calc 1, where really you were looking at integrating across a line that was defined in 1-dimensional space for a curve that existed in 2. Right? We are looking at really a higher or an extension of a very, what would we say here, an extension of an idea up into higher dimensional space. What would we say? We'll leave it at that, right? We're taking this idea of integrating across this line in 1 dimensions for a curve in 2, and extending that up to an integration across a line that's occurring in 2 dimensions across a surface that's occurring in 3. Now, we introduced that idea of a linear integral. That actually is going to come back at the beginning of chapter 17. We'll see a little bit more on linear integration. So we are giving a bit of heads up there too, and that's why I wanted to go through this complete set. And take note, with the linear integral being applied to a multivariable function f and the result being this net area function g in terms of y, we can actually come back and apply this linear operator again, this linear integral operator again, to this result of g of y. And we can apply it in the form the integral from c to d that's going to happen with respect to y. Right? This is going to produce overall in calculation what's known as a double integral. Or in chapter 17 we are going to identify it as a surface integral operation, right? That actually is going to happen in what we think of, in a case that's going to occur over a region that is what's we call a rectangular region, or a region that is going to be rectangular in shape, right? Where the value of this calculation then, right, in the end, in geometrical terms, is going to correspond to a net volume, right? A net volume that's trapped between our surface, this multivariable function, and some rectangular region in the xy plane that is bounded by some lines that occur vertically in 2 dimensions where x equals a and x equals b, right? And some lines that occur horizontally in 2-dimensional space where y equals c and y equals d. And actually, if we consider the region over which this integration is going to occur, right? In 2-dimensional space, it's going to occur over this region R here. That is this rectangular shaped region that can be defined as being bounded by these lines where x equals a and x equals b, and where c equals d and where y equals c and y equals d, right? The region of space trapped between all those lines forms this rectangular region. And we're going to be integrating our surface, right, in 3 dimensions over this rectangular region in 2-dimensional space. In a sense, we're still going to have this surface here in 3 dimensions, but the space over which we're going to be integrating down here in 2-dimensional space is actually going to be a rectangular region, a 2-dimensional description of space, not this 1-dimensional description of a line. All right? We can formally define that as follows. If I bring that definition into view, right, that's defined as follows. Right? By definition, we might assume z equal to f of x comma y is some multivariable function in 3-dimensional space. What we define as the double integral of f over this rectangular region R, where formally we can define R as follows here, right? We might say this is R, where R is represented by the set of coordinates in the xy coordinate space, or we might say R is defined by this set of coordinates in the xy coordinate space, right? Is given by, right, this double integral calculation here, folks. One thing we will note is that this double integral calculation is written in this somewhat arbitrary format. What this arbitrary format does illustrate is what we call the surface integral operator. This double integral over R, right, as we're going to begin understanding it as, is actually a single operator that can be applied to this function f that happens with respect to just variable a, right, big A, capital A, right? We can calculate a surface integral of function f with respect to just the variable a, where big A, capital A, is the variable representing what we would think of as being an area parameter. If we were to remove some of that arbitrary nature to this, right, description of a double integral, that value dA could actually be thought of as the quantity dx dy, or the differential dx times the differential dy, the infinitesimal change in x times the infinitesimal change in y is going to produce an infinitesimal change in area. If we were to consider that in our graph here, what we're thinking of doing here, what we're going to see happen in our description, right? When we jump down into the proof of all this, we are going to subdivide from a to b into n subintervals and c to d into m subintervals, where we're going to be interested in the infinitesimal change in x and the infinitesimal change in y. Well, the infinitesimal change in x and the infinitesimal change in y is going to cause an infinitesimal change in area, we might think of, right? Changing x infinitesimally and changing y infinitesimally is going to change the area of this region infinitesimally. And that change in area is nothing more than the change in the width times the change in the length of that rectangle, we might say, right? And that understanding can occur in any order, which means in terms of calculating this value, right? We do have what's called Fubinis result, or Fubinis theorem. This would be laid out as Fubinis in the chapter, Fubinis theorem, which does say that the double integral of, right, or the surface integral of R over R for function f, all with respect to that area parameter A, can be calculated either as this double integral, right, where we integrate first on the inside of the integral, right, first with respect to y, and then consider the integral with respect to x, or consider that equivalent to integrating first with respect to x inside this double integral calculation, and then with respect to y. Either calculation here, right, is equivalent to the double integral of function f over this rectangular region R with respect to the area parameter. And what it does yield, right, in the end is this net volume. What would be the net volume of space trapped between our surface and the xy plane over region R in the xy plane. All right. I believe I have an illustration of that here. Let me see. Oh, wait, actually, I illustrate this by example, right? We might say here, consider the net volume trapped between this surface, right? Slightly more complex planar surface, right? And the xy plane over the region R in the xy plane defined by this rectangular region, right? Here, x is bounded by the values between 2 and 6, and here y is bounded between the values of 1 and 8, right? All of region R is defined by these xy coordinates that have these restrictions placed upon them, right? The following is an illustration, right, of this setup. Here, if I, for instance, make this illustration a little larger so we can all see it, right? Here we have our surface. This is the surface F, this semi-transparent surface here in three-dimensional space that is highlighted with these square grid on it, right? That's happening in 3 dimensions over this region of R that occurs down here in 2-dimensional space with respect to x and y, right? That region R occurs over values of x from 2 to 6 and for values of y from 1 to 8. And you can see those boundaries for x and those boundaries for y give us this bound on R. And what's trapped between this surface in 3 dimensions and this rectangular region of R down here in 2-dimensional space is actually a volume of space. And that volume of space is what we're going to calculate with this double integral calculation. All right? If we consider the illustration in that case, let me undo the size there. This up into view. All right. As I noted, this net volume is going to be given by this double integral calculation, where in this case we might consider approaching that calculation in this order. Now, this is just an arbitrary order. I just picked to go ahead and start integrating with respect to x first because we are often a little bit more familiar with integrating with respect to x than y. And we would integrate with respect to x across the bounds from 2 to 6, and then integrate with respect to y across the bounds from 1 to 8. And in the end, though, regardless of the order, we would produce what we would call this net volume calculation. Now, folks, this double integral across these definitive bounds is not going to produce a net volume function. It actually gives you an exact net volume. As you can see, that space is rather exact, right, in its size. There's no variable description that's going to bring itself into play here, right? This exact net volume would be given by this double integral calculation, what we might sometimes think of as an iterative integral, an integration that happens through a couple of iterations of integration, first with respect to x and then with respect to y. right? If I was to highlight that integration here, right, it's for that net volume. Oh, careful there. I got a typo here. As for the net volume, right, note that net volume, right, that double integral from 1 to 8 with respect to y, and then from 2 to 6 with respect to x, where we're going to integrate first with respect to x and then with respect to y, is given by this here. Right? Where you can see the way we handle this calculation as we move forward in this calculation, we are going to first integrate with respect to x. The antiderivative of our multivariable function with respect to x is this argument here, where we are going to evaluate that as we had seen in our introductory example across these bounds from 2 to 6, substituting in 6 for x first, and then subtracting from that what we get when we substitute in the value for x, the value of 2 for x, right? And when we do perform that evaluation across those bounds from 2 to 6, the result is actually 8/3 times 5 plus y. Now that 8/3 is going to be a constant multiple, and I bring that out in front as a constant multiple in the calculation, where then I can just consider calculating 5 plus y, right? Keep in mind what that is. That 5 plus y is that net area function that we had learned about initially as our single integral calculation that happened with respect to x. We're going to take that net area function now and evaluate it, right, with respect to y across these bounds from 1 to y. Now this is a single integral calculation, folks, and it's happening across definitive bounds on a, what we might say is a single variable function, right? It's Calc 1 material, right? Integrating that function produces this antiderivative in the brackets here, which we evaluate across the bounds from 1 to 8, substituting in 8 and taking away what we get when we substitute in the value of 1 for y. Multiplying that by 8/3 does in the end yield 532/3. Now, where I should probably say that's 532/3 units cubed in value, right? That is our net volume for this description of space here, folks. This description of space that occurs between this function, right, described by 4 minus 1/6x plus 2/3 y, and this region of R, right, where R is this region of space, this rectangular region bounded between values of x from 2 to 6 and values of y from 1 to 8. Right? I do finish this example up with a little bit of proof. You can read through this. I kind of highlighted the proof to begin with here, right, and how the proof is going to begin. But if I was to roll through the proof here, just to lay it out for you and be a little formal and give you some proof of what is occurring here, we are going to see a very similar proof for this double integral calculation to what we've seen as a proof for single integration, right? To begin with, we are going to consider the net volume trapped between z equal to f of x comma y and the rectangular region in the xy plane defined by, right, R given here in general. Sorry about that. Where in general, right, if we think about this net area, right, this net volume, the way we're going to go about calculating or relying on some calculation to help us calculate this net volume, we go back to the fundamental volume calculation for a right prism. Now, what is a right prism? A right prism might be thought of as a box, right? A box is a description of a right prism, right? It's essentially a three-dimensional shape whose bases are what we would call parallel to each other in three-dimensional space. And we have a very, hopefully a familiar calculation for a right prism, and that is volume is equal to area of the base times the height, folks. If we take the area of a right prism's base, the area of one of those two parallel bases, and we multiply it by the height of the prism overall, it will give us the volume of that right prism. It's a rather fundamental geometric calculation that we are going to rely on here. Now to begin, we are going to begin by subdividing that interval for x from a to b into n subintervals and subdividing our interval from c to d for y into m subintervals. Right? We're going to start by subdividing from a to b into n subintervals and from c to d into m subintervals. What this is going to do is subdivide R. This is going to subdivide R into little subregions. How many subregions we will subdivide R into will depend upon n and our value for m. It's going to be n times m. If I subdivide this into 10 regions, intervals, and I subdivide this into 10 subintervals, that's going to subdivide R into 100 subregions, 10 times 10 of them. All right? So what we note is we state that in the proof, right? This in turn subdivides region R into n times m subregions. Now when that subdivision of R happens, right, into its n times m subregions, what that actually is also going to do is subdivide our solid, this solid whose volume we are trying to approximate, right, or to begin approximating and then finding the exact volume of. It's going to subdivide that into what we might say are n times m sub prisms, right, or sub regions of space. What do I say here? Then it subdivides the total net volume into n times m approximate right prisms. Right? I say approximate because what we will take note is when we subdivide these into prisms, they aren't going to have parallel bases. The bottom, right, is going to occur in the xy plane, right, and be level to the xy plane. But the top of these prisms, these subprisms, are going to be defined by our function f, right, the surface in three-dimensional space, right? So these are going to be approximate right prisms, not perfect right prisms. Right? But there will be n by m of those, right? N times m of them. Again, if we subdivide from 2 to 6 into 10 and from 1 to 8 into 10, we would have 100 regions for R, and this solid would be divided into 100 sub-right prisms. All right? So that's what we're opening up with. Now, that sets us up for defining some things, right? Declaring some values. What we might do is declare delta x then to be the length of the n subintervals for x, and we might let delta y then be the length of the m subintervals for y, as we've seen done in previous proofs involving integration. We will let x sub I be a value of x in the I subinterval of this closed interval from a to b, and we might let y sub j be a value of y in the j subinterval from c to d. Now we do change up our subscripts here. We are going to use I for x and j for y, right? What we were then able to define is any coordinate in the ith subinterval for x and j subinterval for y could be written as this coordinate x sub I comma y sub j, which is really going to be defined then as a coordinate in the kth subregion of R, right? And the approximate volume for the kth right prism in this corresponding subdivision of total net volume, right? The approximate volume for just one little sub right prism would be approximated as follows. And what you can see here is this is where we go back and we rely on that fundamental idea for how do we calculate the volume for a right prism. The right prism's volume we're interested in is going to be approximated by this value. Right? It's going to be the area of the base, which is really just going to be how wide is the nth subinterval of x times how wide is the nth subinterval for y. Those quantities multiplied together will give us the area of the base for the kth sub-right prism whose volume we're trying to approximate. And the height of this kth sub-right prism is going to be given by the value of the function at this coordinate x sub I comma y sub j in the kth subregion of R. Right? If we think about going into one of the sub-right prisms that we can subdivide this total volume into, it's going to have a base, right, whose area is going to be n times m, right? Or I should be careful there. It's going to be delta x times delta y, and its height is going to be determined by the surface f at that coordinate x sub I comma y sub j. Right? Now, that being the area of the base, this being the height, we can do a little rearranging of those factors into a more familiar form. That being the form f of x sub I comma y sub j times delta x times delta y. That should look familiar to some other formal proofs I've done involving integration in the past. We know in those formal proofs, once we develop an approximate of the kth subregion, we can then develop that approximate into an approximate of the total net volume. Total net volume is going to be given by some summation, some Riemann summation. Right? What we're going to form are the Riemann summations, right? First with respect to x across the index from I equals 1 to n being the number of subintervals of x that we've subdivided our closed interval from a to b into, right? And once we calculate that Riemann summation of those values, that is going to result in some function with respect to y, who we're going to come back and form its Riemann summation calculation for with respect to y. That is going to occur across an index of j that starts at 1 and continues up through m being the number of subintervals that we divided y into over that interval from c to d. Right? So that total volume can be approximated by what we might think of as this double Riemann summation. Now, what can we say about that double Riemann summation? I do note that we can make it exact by now applying some limits. A limit where n heads to infinity and m heads to infinity. Actually, we're going to end up applying two limits here, one for the case of n and one for the case of m. If we look at that application, right, it might initially, right, look like this, where we're first going to apply the limit with respect to x, right? Or I should say n, as n heads to infinity, which is going to be considering x changing, and then come back and apply the limit with respect to m, as m heads to infinity, where we're going to be considering the change in y. Now, limits will distribute themselves through summations. So this very first limit, I can distribute it into the very first summation with respect to the summation from j equals 1 to m. It can distribute itself into that summation. So it can be distributed in and thought of as being applying itself to just the summation for f times delta x. Delta y being a constant multiple, it can be factored out of a summation. So it's going to be factored out of this summation here that's happening with respect to just n, from 1 to n. Right? This inner limit, right? That should look familiar, where we can come back and apply the definition of a definite integral of that limit of a Riemann summation on the inside of these brackets, which is going to produce an integral calculation. That value corresponds to the linear integral, or the single integral from a to b for function f of x comma y sub j times delta x, where we then can come back and take that integral's limit of a summation, and that is going to correspond to another double integral calculation. In fact, if I bring that note into picture, we might note from the definition of the definite integral, this inner limit of the Riemann summation will produce this integration, right? Which we have seen several times in past formal proofs, where what is this is nothing more than a function g of y. Right? A single integral applied to a multivariable function with respect to variable x, as we had noted at the very beginning of our notes, just produces some net area function with respect to y. It's just a function with respect to y. In this case, the function with respect to y sub j in our scenario. Right? Where with respect to y sub j, we can now come back and consider the limit of that with respect to y. And in fact, if I wanted to add a line in there to maybe highlight this, we could consider finding this equal to the limit as m heads to infinity for the summation from j equals 1 to m for what is going to be, in a sense, now g, big G of y, right, sub j. That's going to occur, be multiplied by, now the value delta y can come back in as a constant multiple into a summation. So I bring that into the summation and consider this as our calculation, the limit of this, where from the definition of the definite integral and how we transform this inner integration, right, into this definite integral calculation, this limit of the Riemann summation for this function big G of y sub j times delta y can translate itself into this calculation here, where we might say, well, this is going to be equal to the integral from c to d for what is function big G of y, all integrated with respect to y. Right? And what do we know about big G of y? Big G of y is equal to the integral of big F of x comma y integrated with respect to x. Right? And since we might say here, big G of y equals the integral from a to b for big F of x comma dx, right? This quantity we know as the exact volume, V, can be calculated using this double integral calculation, right? So folks, that is the formal proof of double integration in the context of rectangular regions. I don't know if I'm going to have time to go through all of the proofs for each of the different scenarios we have, but they will happen very similar to how I set this up for the proof of net volume by double integration over rectangular regions. And this being the simplest of cases, I definitely wanted to make sure I spent the time proving this. All right, folks, this is my, again, Calc 3, folks, this is my first lecture in what is going to be a series of lectures over Chapter 16, followed up with some Chapter 17 lectures, all in a hope to help you cope with having to move into these online studies. I hope you're safe. I hope you're doing well out there. If you have some questions, you know how to get a hold of me. But hang in there, folks. We're all doing the best we can to get through this. So, I'll see you in the next video.